Let's illustrate the significance of dx, of the with respect to variable. An indefinite integral is supposed to be a function, but a function of what variable? The differential notation, the dx, which is the differential notation that's incorporated into the indefinite integral notation, answers that question for us. The dx indicates that this indefinite integral represents a function in terms of x. That's what this means, with respect to. This says find the antiderivative of x squared with respect to x. The defining property of this function of x is that its derivative with respect to x is x squared, which is the integrand. And here, these last two examples will illustrate the importance of the with respect to. Because if the with respect to differential notation wasn't there and we were given an integral like this, well, is this a function of z or is this a function of s? Here, the symbol z may represent a constant, or it's going to be treated like a constant as far as the variable s is concerned. So regardless of the meaning of the symbol z, the integral represents a function of s. We know this because ds tells us it's with respect to s. Okay, and constants pop out front. So this could literally be z times the integral of s to the fifth ds. So that is the importance that the differential notation is playing in the indefinite integral. We'll see when we get to the definite integral, because there's a different integral we'll be using, that the differential notation, the dx, dy, dt, whatever, actually has two roles. It has a with respect to role, and it plays another significant role beyond that. All right, so here formally are three rules for antiderivatives: the power rule, the sine rule, and the cosine rule. So we've already talked about the power rule quite a bit. Make up a flashcard if you need to, but by the time you get to class next time and start to do homework, you're going to be responsible for knowing the power rule for integrals. The integral of the sine of x with respect to x, what did I take the derivative of to get positive sine of x for an answer, was negative cosine of x, and again, there could have been a constant there. So make sure that these positive and negative signs don't drive you insane. And the antiderivative of cosine is positive sine, because the derivative of positive sine is positive cosine, and the derivative of negative cosine, the derivative of a positive cosine, is a negative sine. So that's why this antiderivative is a positive sine of x. So watch those negative and positive signs very carefully. The more and more and more involved our anti-differentiation gets, the easier it is to drop those positive and negative signs. So watch that carefully. And again, you're responsible next time you come to class. When we do homework over this lesson, you're responsible for knowing the antiderivative of sine and cosine, not just the power rule. So let's explore some more properties of integrals, of the indefinite integral. They have properties or rules just like derivatives had. So we'll formally explore the rules that integrals follow in a later lesson. I'll give them all to you. But for now, let's just kind of intuitively see what's going on here. We've already seen examples that we know integrals break up over addition and subtraction. So that's a rule or a property that we already know. One that we really haven't seen an example on, it turns out that the power rule for integrals works for fractional exponents just like the power rule for derivatives did. So this says find the antiderivative of this function with respect to x. Well, we can apply the power rule to that, even though that exponent is not an integer, even though it is a fraction. Now, here's one thing we haven't seen. This is a quotient. This is some derivative function that when we took the derivative of whatever that original function was, the result was this quotient. And integrals, just like derivatives, do not break up over division. It turns out they do not break up over multiplication either. All right, so just like derivatives don't break up over multiplication or division, integrals do not either. So that means we're going to have more rules or more techniques for finding our antiderivative functions than just straightforward power rule and things like that. So just like we had the product rule and the quotient rule for derivatives, we're going to have different techniques for finding antiderivatives when the product rule or the quotient rule were used to find the derivative in the first place. So a big part of what we're going to do when we find our antiderivative functions is to undo the chain rule. If we found a derivative where the chain rule was used, the way to find our antiderivative is going to involve this technique called u-substitution. U-substitution, huge. So when Professor McCowan says it's huge, it's all over the AP test. You know what that means. You got to know it, you got to know how to do it, and you're probably going to see it pretty quick. Most definitely on homework and definitely on quizzes and exams. So let's look at a power function times a derivative. Let's say I have some function f of x, and it is raised to the power of n. In other words, it is a composed function, okay, whatever it looks like. And it's multiplied by the derivative of the function that's inside. All right? When we have that going on, and we want to find the antiderivative, the function that we started with, the one that we took the derivative of and had this for an answer, this is going to involve undoing the chain rule. Because remember, integrals and derivatives are inverse operations. They undo one another. So if the chain rule was used to find the derivative function, then u-substitution is a technique we're going to have to use to find the antiderivative function. All right, so let's look at how we get through u-substitution. If we find ourselves with a function that is raised to a power and inside the integrand we have the derivative of that function, then it is kind of sort of like a stylized, if you can see this here, a stylized power rule just for a power term. It's 1 over n plus 1 times not just x, but our function in x raised to the n plus 1 plus c. So if we have a derivative function that once we found the derivative, it resulted in that result, if that's our integrand, then we're going to use u-substitution and we're going to find our antiderivative function using this. So again, make up a flashcard, whatever it is that you need to do. I'm not real sure that I want you to memorize this as much as I want you to internalize the process for applying u-substitution. So I don't know that I would make a flashcard up over that and memorize that, because the process for u-substitution is fairly straightforward. So what we're going to do here is we're going to rewrite our integrand and we're going to try to simplify it, and that's where u comes in. That's why it's called u-substitution. We want to rewrite that integrand in a simpler form so that it's easier for us to find the antiderivative function. So let's say we called f of x u. So everywhere in that integrand that f of x is written, we're going to write u instead. So f of x is raised to the power of n, so we're going to write u to the n. Now, I'm going to ignore what's happening up here for this next step. For this step, du, the derivative of u, has nothing to do with what's going on inside your integrand. The derivative of u, du dx, comes from what your choice for u was. It comes from f of x. So the derivative of u with respect to x is f prime of x. If I multiply both sides by dx, now I have du. And I want to completely rewrite this integrand, that integral, the whole integral, in terms of u and du. So that if I was to pick up a different color and back substitute what I chose for u, and I chose u to be f of x, and what I chose for du, if I back substitute that in here, and we chose that to be f prime of x dx, we didn't choose it to be, we found it to be that, then I know that that substitution better get me back to the original integrand that I started with. Again, u-substitution is taking something very complicated and simplifying it. Because now, finding the antiderivative of the integral of u to the n du, well, that's the power rule. That's 1 over n plus 1, u to the n plus 1, plus c. And I'm going to finally substitute back into the terms of the original variable. So that's 1 over n plus 1, f of x to the n plus 1 plus c. And that should look familiar. We just had that written on the last slide. And this is where that comes from. Again, I don't so much want you to memorize this as to internalize the process. And we'll do some examples so you'll see exactly what the process is. But you are going to, and I say this every year and students giggle, but this is just how I've always said it, you bring u to the integral party, so to speak. So the very last step right here, you have to take u home. All right? It's just the nice thing to do. So we're going to rewrite our integrand in terms of u and du because we want to simplify something very complicated. We want it much more simple. We're going to use it to find our antiderivative function in terms of u. And then we're going to substitute our original substitution, our original choice for what u was. We're going to substitute that back in here so that we actually do have the antiderivative with respect to the original variable. All right? I know that's very theoretical and it's maybe hard to follow with f of x to the n and u and du and du equals f prime of x times dx. You'll begin to see that it's not that terribly complicated when we get down to a specific function, a specific example. But u-substitution is going to be the go-to technique for evaluating a lot of our integrals. Now, we've actually already talked about this. I wrote all this on the prior slide. So again, we want to simplify our original integrand, write it in terms of u and du so that it is exactly the same, has the same value as the original integral. Then we use the new, more simplified indefinite integral to find our antiderivative function, and then we take u home. We brought u to the party, we take u home. Here is an exact example. I'm at the end of my time, so on the next video we'll work these examples and we'll finish up this lesson.